Hey Global Impact students, in this lesson we're going to look at compound inequalities. Our learning targets for the lesson: we need to be able to solve and graph inequalities containing the word and we need to be able to solve and graph inequalities containing the word or. Central understanding for the lesson: the solutions of a compound inequality are either the overlap or combination of the solution sets of distinct inequalities. Also, the graph of a compound inequality with the word and contains the overlap of the graphs of the two inequalities. The graph of a compound inequality with the word or contains each graph of the two inequalities. Background: to satisfy the inequality x is less than 7, a number only need to be less than 7. To satisfy a compound inequality, a number may need to meet two conditions. These conditions are either expressed by the word and or the word or. So we find the solutions of a compound inequality by either identifying where the solution sets of the distinct inequalities overlap, or by combining the solution sets to form a larger solution set. So here on the left side we have the graph of a compound inequality with the word and containing the overlap of the graphs of the two inequalities that form the compound inequality. So a compound inequality just means multiple inequalities. So instead of just having x is greater than or equal to 3, we're going to look at a compound inequality that has two parts to it, where x is going to be greater than or equal to 3 and x is going to be less than or equal to 7. So here is our compound inequality. And we're going to solve these here in a minute. So we're going to be looking at these two conditions together, not solely by themselves. So when we put these two conditions together with the word and, whatever is a solution to this compound inequality has to fit both of these conditions, not just one. So here's what the graph of x is greater than or equal to 3 looks like. We got a closed dot on 3, graph to the right. The graph of x is less than or equal to 7, closed dot on 7, everything to the left. Now if I were to lay those two graphs on top of each other, where they overlap is between 3 and 7, including 3 and 7. So that's what this green graph represents. So everything that's in between 3 and 7 inclusive would be solutions to this compound inequality. Over here on the right, we have the graph of a compound inequality with the word or. So here we have two inequalities: x is less than -2 or x is greater than or equal to 1. So a compound inequality, two inequalities together, but this time with the word or. The difference between and or in an or inequality, our solutions only have to satisfy one or the other, not both. All right? So x is less than -2, open circle on -2, arrow going to the left. X is greater than or equal to 1, closed dot on 1, arrow going to the right. If we put those two graphs on one graph, again that's our green graph here, we have an arrow going from -2 to the left with an open dot, closed dot from one, arrow going to the right. That's the graph of that compound inequality. So you can see an or problem, we're going to have two parts. Okay, compound inequality, we're going to have one part. So we can rewrite a compound inequality involving and as a single inequality. For instance, in the inequality above, right here, you can write x greater than or equal to 3 and x less than or equal to 7 as 3 is less than or equal to x, which is less than or equal to 7. Okay? And like I had mentioned before, another way to read it is x is between 3 and 7, inclusive. And recall, the word inclusive means if you're talking about 3 and 7, you're including 3 and 7 in that solution set. So some examples. What are the solutions of -2 less than 3y minus 4 less than 14? Graph the solutions. So here we have a compound inequality. This is going to be an and inequality, even though we don't see the word and. Anytime we have our variable expression in between two numbers, one on the left, one on the right, we know it's going to be an and situation. So here's one way that we do this. Create two inequalities, write it as an and problem, and solve them. Solve for y, We're going to add 4 to both sides. So on the left side we get negative 2 plus 4 is 2. On the right side we get 3y. Divide both sides by 3. We get 2/3 is less than y. Over here we're going to add 4 to both sides again. That gives us 3y on the left. This gives us 18 on the right. 14 plus 4. Divide by 3. Y is less than 6. So our solutions here have to be greater than 2/3 and they have to be less than 6. So on the graph, if I put 2/3 here and I'll put 6 out here, I'm not worried about the scale of this, just a visual representation of what's going on. Open circle or open dot on 2/3, open dot on 6. Everything in between is the solution to this compound inequality. So this is one way. Let me just show you the other way you can work with these and compound inequalities. I'm just going to work with it as it's written. Negative 2 less than 3y minus 4 less than 14. What I'm going to do is I'm just going to, instead of breaking this up into 2 separate inequalities, I'm going to work with this all together. I'm trying to isolate y. This time I'm trying to isolate y in the middle, because remember, graphically, our solutions are all y's, or all values in between these 2 values. So we're just basically going to try to isolate y here in the middle. So I'm going to add 4. I have 2 inequalities now. So I'm going to add 4 here, and I'm going to add 4 here. I get 0 in the middle. Okay, I get a 0 out of this. So negative 2 plus 4 is 2, less than 3y, less than 18. Divide everything by 3. So I get 2/3 is less than y, which is less than 6. All right, so I can work with them together simultaneously. All right, my next example is an OR problem, and I can't do what I just did here with the AND problem. I have to work with these separately. Okay, so my first one on the left here, I will isolate y. I'm going to subtract 7 from both sides first. This part's a 0. Bring down the negative 2y. Less than 1 minus 7 is negative 6. Divide through by negative 2. I know I'm going to switch my inequality. Negative 6 divided by negative 2 is 3. So part of this is y greater than 3. My second inequality, I'm going to subtract 3 from both sides because I'm adding 3. Bring down the 4y. I'm trying to isolate y. Negative 5 minus 3 is negative 8. Divide through by 4. Y is less than or equal to negative 2, because negative 8 divided by 4 is negative 2. So here my solutions are y greater than 3 or y less than or equal to negative 2. So here's negative 2. Over here is 3. Greater than 3. Open dot, arrow to the right. Less than or equal to negative 2. Close dot, everything to the left. There's my graph. These are my solutions. Here's the visual representation of that. So any value that falls in this part of the graph is a solution. Another example. For parts A and B below, write a compound inequality that represents each phrase and then graph the solutions. So in A here, we've got all real numbers that are greater than or equal to negative 4 and less than 6. So it's an and problem. So we know that our solutions are going to be greater than or equal to this, less than this. So in A, I'm just going to write negative 4, x less than 6, right? X is between negative 4 and 6, including negative 4, but not 6. Graphically, if I put negative 4 here, I will put 6 all the way over here, including 4, so a dot, close dot, not including 6, so an open dot, everything in between is a solution. Part B, all real numbers that are less than or equal to 2.5 or greater than 6. So x is less than or equal to 2.5, or x is greater than 6. So if this is 2.5, and this is 6 out here, less than or equal to would be a closed dot, everything to the left. Greater than 6 would be an open dot, and to the right, greater than 6. So here's an application of some compound inequality here. Suppose you score 78, 78, and 79 on the first 3 tests. Is it possible for you to earn a B in the course? Assume that 100 is the maximum grade you can earn in the course and on the test. Also need to assume that an 80% to earn a B. Okay, so we're talking about a traditional setting. We know B's, we don't do B's here at Global Impact. A work is what we're shooting for. How would we do this? Well, we know that a B on a typical scale is going to be between 80 and 90, right? The grade could be equal to 80, but it's going to be less than 90. What are we going to do with these? Well, we're going to calculate the average, right? So 78 plus 78 plus 79 plus our 4th test score, which we'll call x, that average, so divide by 4, has to be somewhere in this range. 78 plus 78 plus 79 is 235. So we have 235 plus x over 4. And that has to be somewhere in between here. Greater than or equal to 80, less than 90. So the way that we solve this, x is in the numerator of our fraction here. So the first thing we'll do is multiply both sides by 4. 80 times 4 is 320. And 90 times 4 is 360. So we will subtract 235 here, here, and here. That gives us 85 on this side of the inequality. X is alone in the middle. This gives us 125 on the right. Is it possible for you to earn a B? Well, this statement here that we just came up with says you have to get at least an 85. Now, mathematically, it says up to a 125, but we know that this is not realistic unless your teacher gives you a ton of extra credit on the test. It's safe to assume that our score has to be between 85 and 100 to get the B. So it's possible. You just have to get an 85 or higher. Another thing you could assume here is that there's no way to get it up to an A, right? Because just to get less than 90, we'd have to get a 125. So to get over 90, we would have to get more than a 125. And as I said before, unless we have a ton of extra credit on a test, not going to happen. So here is our other type of notation that we use to write inequalities and solution sets of inequalities. We can use an inequality such as x is less than or equal to -3 to describe a portion of a number line called an interval. You can also use interval notation to describe an interval on a number line. Interval notation includes the use of 3 special symbols. These symbols include parentheses, so we'll use parentheses when a less than or a greater than symbol indicates that the interval's endpoints are not included. We can use brackets, I call them square brackets. We can use these 2 symbols when a less than or equal to or a greater than or equal to symbol indicates the interval's endpoints are included. And then another symbol, we've talked about the word infinity a few times here. So we'll use the symbol for positive infinity when the interval continues forever in a positive direction. And when things decrease towards what's called negative infinity, we'll just put a negative sign in front of the infinity symbol, which implies that the interval continues forever in a negative direction. Is infinity a number? And we will discuss infinity in this concept a lot more, but let's go ahead and talk about it right now, just initially here. This is actually a concept that we'll get into much more in when we get to calculus, but let's talk about a calculus concept a little bit right now. Is infinity a number? And the answer to that is no. Infinity is a concept. When things go on forever in a positive direction, we call that infinity. What it means is that the numbers are increasing without bound. There is no limit on the numbers going up, if you will, in a positive direction. And the same thing with the negative infinity. We are saying that numbers are decreasing without bound. There is no limit to how far into the negatives we get. There is no limit to how far left on a number line we get. So this is just to say this is going to keep going forever in a positive or a negative direction. So infinity is not a number, okay? And that's going to be key on the part that we're going to look here in our interval notation. So an inequality x is greater than or equal to 2 on a graph has a closed dot on 2, graph to the right. So the interval notation, the start of that endpoint or that interval is 2, including 2. So we put the 2, square bracket. It's going to positive infinity. It's going on forever to the right. So we put the infinity symbol and then a parenthesis. We always put a parenthesis on an infinity or a negative infinity because, again, it's not a number. So it's not an endpoint of an interval. The interval continues on forever. So square brackets on infinity do not even make sense because there is no end to the interval. X is less than 2. We have an open dot on 2, arrow to the left. So this is a graph that's going forever in the negative direction. It's an interval that is, the values are constantly decreasing, getting more and more negative, if you will. So from the left end of the interval over here, there is no real end. So that is a negative infinity situation. The right end, if you will, of the interval is 2. The 2 is not included, so we put a parenthesis because it's just less than 2. Okay, here we have x is between 1 and 5, including 5. So we have an open dot on 1, a closed dot on 5. So our interval shows everything between 1 and 5, not including 1, but including 5. Here in an OR inequality, x is less than -3 or x is greater than or equal to 4. Here we have open dot on -3, everything to the left. So that's this portion of the interval, everything from negative infinity up to -3, not including -3. Or everything from 4 to positive infinity, but including 4. So we'll put a square bracket on 4. All right. So OR inequalities will have 2 separate intervals. And inequalities will have 2 numbers in here, and everything in between those 2 numbers are solutions. Single inequalities will have infinity in either positive infinity or negative infinity. All right, so what is the graph of -2, 7, including 7? How do you write -2, 7 as an inequality? Well, like I just said, when we have numbers in here and both endpoints, here's -2, here's 7. It's everything in between with an open circle on, or an open dot on 2 and a closed dot on 7, everything in between. So that's an inequality that is -2 is less than x, which is less than 7. Have a good day, folks.